We're going to talk a little bit more about concavity, points of inflection today. I think we're going to do one more problem together, and then we're going to look at the second derivative test. Okay?
Yes.
What do we use the first derivative test to find? Okay, and then ultimately we use that to then find...
Relative minimum.
Okay, yeah, so ultimately, relative extrema is what we use the first derivative test to find, right? The second derivative test is going to use the second derivative to find relative extrema still of the original function. So believe it or not, okay, we can use the first derivative to find relative extrema of the original function, and we can also use the second derivative to find relative extrema of the original function.
Is there other extrema besides the minimum and maximum?
The ones that we'll have to deal with, no, not extrema. Yeah, we're only going to worry about relative mins, relative maxes, and then absolute mins and absolute maxims. Okay? And then, so let's do one more practice point or problem here with the concavity and points of inflection. Okay? So, we'll just jump right in here. So we're going to find the points of inflection of g of x, excuse me, equal to 1 over 1 plus e to the negative x. Okay. And we're going to determine the concavity of g as well. Okay, so I gave us a nasty one here. So our original function here, g of x, is 1 over 1 plus e to the negative x. Okay? So, Mac, what might be helpful for us to do here before we take the derivative? Exactly right. Rewrite it. Okay? If we leave it like this, what will we have to do when we take the derivative? What rule will we need to use? Quotient, right? Written like this, do we need to use the quotient rule now? No, it would just be the what? You just do it. It would be the chain rule, okay? But yeah, you do just do it. Okay, like Nike. All right, here we go. And Mac, guess what? You're going to just do it. Okay, so g prime here. What's the first derivative going to be, Mac? Okay, I'll let you write it down. That's right, stall for time here so you can think about it. I got to write it down, Mr. Wood. 5 minutes later. All right, I got it written down. No, I'm just kidding, Mac.
The
Yeah.
first part, like 1 plus e to the negative x.
Okay.
Sorry, negative 1 in front.
Yeah, so right, we have a power, right? Something raised to negative 1, so the negative 1 goes out front, leaving.
1 plus e to the negative.
And then what's our new exponent?
Negative 2.
Yeah, very good. Don't forget those exponents, right, everybody? Times e to the negative x, almost, times the derivative of what's inside that, negative 1. Mm-hmm. Why is there a negative 1 here?
No, go upward. Why is the x so negative?
Oh, because it was negative in the denominator, so when we raise this whole thing to the negative 1 power, it still stays a negative x like that. Is that good for you? Okay, so let's simplify this sum, right? So let's see here. Ryan, how can we maybe simplify this a little bit before we jump right into taking the second derivative?
All right, well, you could first make it the second part of it, negative e to the negative x.
Okay, and then that negative e to the negative x, that's going to multiply with that negative 1 out front here to make it just what?
E to the negative x.
So just positive e to the negative x. So it becomes e to the negative x times 1 plus e to the negative x to the negative 2, like that.
Right.
Okay?
Correct.
Now,
don't see any other ways.
Yeah, there's not a whole lot here, okay? What I'm going to do, actually, for some reason, I don't want to do a product rule here. I want to make this a quotient rule. For some reason, I prefer it as a quotient rule. So, if you want to do it as a product rule, you're welcome to, but I'm going to rewrite this as... Oh, wait a minute. Wow, I really did do that weird. That's funny. Because I should put the e to the negative x in the denominator, too. Alright, forget it. Let's do a product rule. We'll do the product rule. Okay, here we go.
Wait, did you just not want to do the product rule because you had the answer on your paper?
Well, I
We
mean,
have the same answer either way.
when I do my notes, Brittany, oftentimes I do things in a particular way for a reason. So, in this case, though, I don't think I really did it for a particular reason, so I'm just going to do it this way. I can still do this, Brittany. Don't you worry about that, okay? So, alright. Let's pick somebody else here. Some other victim or volunteer.
One of the smallest baby airplanes.
Oh, thanks. Cute. Alright, Nate! Shh. Alright, so when we go to take the derivative here, Nate, we're going to use the product rule, right? So go ahead, what's it going to be? Shh. And here's the first thing, here's the second thing, right? So what... That's okay. So the first, so what's the first?
Oh, I always do the second.
Okay, so the second, so the second, so that's going to be 1 plus e to the negative x to negative 2 times the derivative of the first, which is what?
Negative e to the negative x.
Negative e to the negative x, very good, plus the first, so e to the negative x, right, times the derivative of the second. So what's that going to be?
Which is negative 2, 1 plus e to the negative x in parentheses times negative e to the negative x.
Okay, almost. What's your exponent?
Negative
Yeah, don't forget the, I think you just, I don't know if you,
2.
Alright.
yeah, negative 3.
So close.
Yep, so, good.
Gonna need a calculator for this.
Okay. So again, we did this. So again, for product rule, it doesn't matter. You can do the first times the derivative of the second plus the second times the derivative of the first, or you can do the second times the derivative of the first plus the first times the derivative of the second.
So this would be a calculator problem, right?
Where do we need a calculator for?
Well,
Yeah, it would be nice to have.
hang on a second. Maybe
I don't
not.
see any reason to
I
use a calculator.
That's right. Yes. No.
I
Just,
think you're right. I think I get it now.
yes.
It wouldn't help us.
I really don't even.
Let go, Ryan. Let go of your technology. Okay.
Wait.
Use the force, Ryan. Okay. So, if we look at what we have here, let's simplify this sum. Shh. All right. Do we see anything in common? We really only have two terms here, right? Separated by addition. There's your first term. There's your second term. Do we have any common factors we can pull out? Okay, yeah, both have a negative e to the negative x, so let's factor that out. All right. And then, all right, let's just do that for right now.
Oh, wow, this is fun.
Well, because I don't want to do it too many steps at once here for you guys, so we'll just... It's no, absolutely, yes. In calculus, the general, some of the derivatives can be tricky, but really it's the algebra, that's the simplification and stuff like that. Okay? So again, take it one step at a time. Do not feel the need to jump a billion steps. Do what you need to do. Okay? Take up a whole page. I will get you more paper. I will get you another pencil. I promise. I can't get you another hand. But okay. Right. Anything else in common that we can pull out?
1 plus e to the negative x.
Yes. And which power are we going to pull out here?
Negative 3.
Negative 3. So I think, Chanda, actually, you asked about this one earlier, right? When we have a negative 2 and a negative 3. When we have a negative 2 and a negative 3, negative 3 is the lower of the two powers, so that's what we're going to pull out, is the lower of the two. Okay? Okay. All right, so we factor out that 1 plus e to the negative x to the negative 3. What's that going to leave from this term then? Just going to give us a little side work up here. I'm taking 1 plus e to the negative x to the negative 2. I'm dividing or factoring out 1 plus e to the negative x to the negative 3. So negative 2 minus negative 3 becomes positive 1. So it just becomes 1 plus e to the negative x. Yeah, and the way that kind of the reason why it works that way is because in one term, we're taking the derivative of that thing, so we're lowering the degree by 1, and the other term, we're leaving it, right, in the product rule. So that's why you always tend to have one that's lower by just 1 degree. So, yep. And then what's left here? Just negative 2e to the negative x. Okay? So, this, where they're being multiplied there, so we're going to leave those. Can we combine the like terms in here? Yeah. These two are like terms. What's positive e to the negative x plus negative 2? Yeah, exactly. And so it becomes negative e to the negative x times 1 plus e to the negative x to the negative 3 times, and then 1 minus e to the negative x. All right. So now, both of these terms have negative exponents. So that means they can go where? In the denominator. So we have a negative e to the positive x now, times 1 plus e to the negative x to the positive 3.
Yes, so I didn't get
Make sure I did that right.
I did somewhere.
Yes, that is correct. Okay, so there it is. Wow.
I didn't get that.
I didn't get that at all.
That's what I get for trying to do the problem.
Well, yours might be correct still. It might just be manipulated in a different fashion than mine, too.
So I got negative e to the negative x over 1 plus e to the negative x.
So, now we've got our second derivative, somewhat simplified. We want to do what with this now? Set it equal to 0, or when it's undefined. So we'll set the numerator equal to 0. We'll set the denominator equal to 0. Okay. All right, so let's see here. I'm gonna add e to the negative x to each side, so I get 1 equals e to the negative x.
It's not going to happen.
And then what do I do?
Nothing.
How can I cancel out the e here? Natural log both sides. What's the natural log of 1?
0.
So 0. And natural log of e to the negative x is negative x. So x is 0. Caleb also was able to see here that if you kind of just look at e to the negative x and 1, well, the only way you can raise something to a power and get 1 is if it's to the 0. So x would have to be 0. You can see it that way too. Yep. Is that what you were thinking, right? That's true. So x is 0. Whoa, we got a critical point. Or, well, a potential point of inflection, I should say. Okay? And then here, let's see. How do we go about solving this?
Split it up.
Yeah, if they multiply to make 0, that means negative e to the x could equal 0. That means 1 plus e to the negative x quantity cubed could equal 0. Will negative e to the x ever equal 0?
No.
It can't, right? You're raising e to a power. E is like 2.6 something to a power. It's going to never be 0, so not possible. Here we'll cube root both sides. So you get e to the negative x equals 0 still. Okay.
Subtract 1.
Subtract 1. Okay, and again, we can kind of see here at this point where it's also kind of a dead end. E is a positive number. Raised to an exponent, positive or negative, it will never be negative, so it can't equal negative 1. If you did natural log of both sides, too, you'd be natural logging negative 1. You can't take natural log of negative 1, so again, we throw those out. And so 0. All that for 0.
Who comes up with these to like make it work like this?
Well, the authors of the book. So.
How would they? I don't even know how to start.
Yes, exactly, because you want the derivative, second derivative to be 0 or undefined. Just like when we do critical points for the first derivative for relative extrema, right? You want the derivative to be 0 or undefined. 90% of the time when we do these, Tyler, 90% of the time we're only seeing when the derivative equals 0. The derivative would just never be undefined. But I never want us to get in the habit of just assuming, oh, it's only when the derivative equals 0. Also when the derivative is undefined. Okay, we're going to check g prime prime. All right, so what might be a good number to pick here?
-1.
All right, let's try g prime prime of -1. And we'll try g prime prime of positive 1. Yeah. Okay, so again, I'm going to look to my kind of like factored version here. All right, my factored version. So let's see, if I plug -1 in here for the x in the numerator, -1, +1, e to the 1, that's like what? 2.6 something, right? 1 minus 2.6 something is what? Negative in the numerator over e to the -1 is 2.6, or 1 over 2.6, but it's negative because you got the negative e to those. So it's negative times then, now we got to do in here. So negative -1, +1, e to the +1, 2.6 something plus 1, still positive, cubed, still positive. So we have a negative times a positive, which is negative. Negative divided by negative, positive. Okay? So no calculator necessary. Right? All right, let's try the second one here. 1. Okay? So now if I plug 1 in, e to the -1 is like 1 over 2.6. 1 minus 1 over 2.6 is, wait a minute, 1 minus 1 over 2.6. So it'll be positive in the numerator. Okay? Plugging 1 in here, e to the 1 is, 2.6, but it's negative, so it's going to be a negative. And then 1 plugged in here, e to the -1 is 1 over 2.6, plus 1 is positive, cubed is still positive. So we have a negative times a positive is a negative, positive divided by negative is negative. Okay, so it's negative there. All right. All that analysis. Brandon. G is concave up for what interval? Just go with the signs.
Okay, so then, negative base is 0.
Yep. Yeah, don't overthink it. Concave up, you're looking for when the second derivative is positive. Okay. Concave down. Brandon?
From 0 to infinity.
0 to infinity. And if we wanted to justify the concave down, we would say G is concave down from 0 to infinity because what? G prime prime, but yes, I know, right? I know, you just about get it, and then like, no, yeah, it's G prime prime is negative on that same interval. Yes, exactly right. And then we would for G is concave up on this interval because that's all you got to do. Yeah, that's it. That's what it means. Yep. Okay, great. And so Austin, does G have a point of inflection?
It does.
G has a point of inflection. No abbreviation here, folks. I don't want to see any POI.
That's what I did on all my homework.
If you feel like you can do that, but some students I know in the middle of the test, because, they're like thinking about all the other stuff, they're going to put POI. I'm going to be like, oh, I'm going to take a point off. Okay, so. Yes. Because you're not supposed to abbreviate, and I'd rather sting you there than on the AP test, okay, where, it's going to really count.
Point of inflection.
If you give them an A on the pen, they just like throw
Inflection.
If you say that, then that's okay. But again, it's like you've already written the word point of inflection to make the key. True. So anyway, where's the point of inflection there?
Random word.
That's right. At x equals 0. Austin, if we wanted to find the y coordinate, like if we wanted to find the actual coordinates for the point of inflection, what would I do? Listen to this, guys. If I wanted to find the actual coordinates, so right now Austin is correct in saying that G has a point of inflection at x equals 0. If I wanted to find the actual coordinates, though, what would I do with that 0?
Plug in 0 to the original function.
To the original function. The point of inflection is a point on the original function. So 0 would go back up in here, which actually is very doable. What is the y coordinate going to be?
It's just going to be 1.
Yeah, so it's going to be 0, 1/2, if you wanted to. So, I mean, that's pretty easy, yeah? All right, let's take a look at it, because this is nutty, right? And so let's just see.
Nutty.
Okay, so let's graph this and see what it looks like.
What if your calculator came with like a message that said no?
Calculator said, no, I'm sorry, I won't graph that for you.
I'm not that smart.
All right, so
Trick me up, man.
this is kind of hard to see. Let me see. I'm going to adjust my window here. I'm going to not go so high on my y-axis maybe and see if we can get some better looking
It does look like 1/2.
behavior there. So, can you guys see the concavity there? Okay, from negative infinity to 0, does it look like it's concave up? It does look like cup-like, right? Maybe I can get my window even better here. Let me adjust it to just like go up to like 1.1 maybe, and we'll go down to just -1 there. Make it more pronounced. There we go.
Hey,
How about that? Okay.
What's up for that?
So concave up, and then at 0, 1/2, it changes to concave down and kind of flattens out. Now it doesn't go exactly horizontal, but it gets so close to horizontal the calculator just makes it horizontal. Okay? So there are calculators that can take like the second derivative like symbolically like this. So
Yep.
yeah. And actually your calculators can take the derivative and graph it.
Can you just take the derivative?
You can either take the derivative of the first derivative, graph it, and then it'll be like
Yes, but it really makes your calculator chug. Like it like
You see,
like if I show you it would like make it. Well, actually I'll just show you here real
Yeah.
quick.
your
Let me just show you.
starts coming
All right.
inside of your
So
calculator.
this, remember, is the original function, right?
Oh boy, okay.
Let me, let's see here. All right, whatever, I'll just go ahead and do it. Okay, so if you guys recall, I'm going to change my mode here to back to pretty type. Ooh, I'm on. Yeah. So I can do math print, which makes it pretty. I'll show you here why in a second. So, all right, so I'm going to do, if you guys remember, the way to do the derivative numerically in your calculator, you can use second trace the dy dx command if you put it in y equals, or you can go to math, and then I think it's num, and then go down to, nope, I'm wrong. It's just in math. N derivative. Now you see, when I do the N derivative command, mine comes up with this pretty thing right here.
How do you do that?
How do you do it?
Can we do that on our calculator?
If your calculator has the mode math print, then yes, you can.
Okay.
Okay? Anyway, I'm here, and so I'm going to take the derivative with respect to x of my y1. Now, I could retype my function here, but you want to see something even cooler? I can go to vars, the vars button right here, go to yvars, function, and there's y1. So whatever I have typed in y1 is now going to be in here. And then if I just put in x is equal to x, so this should now graph the first derivative of that function, but I don't want the first derivative, I want the second derivative, so I got to do math, do n deriv again.
Of y2.
Oh shoot, it didn't fit inside.
Why don't you just do,
I'll have to do, I know I can do, hang on.
yeah, you could
Oh, I could just delete it all and make that work for nothing.
Control-Z,
That's
Control-Z,
one way.
Control-Z.
I know, right? I was looking for Control-Z. I was like, how do I Control-Z? I can't Control-Z.
It's not possible.
There's been so many
It's
times on my calculator where I've just
Oh, it worked.
done something
Okay.
like that and
So then, why don't you just
Derivative within a derivative, bars, y bars, function y1, x. Oh, let's see how much this makes my calculator chug here. All right. So here we go.
Come on,
It's just like-
calculator.
The first one, no problem. The second one,
slower, but
come on, little buddy, you can do it.
I
It's
think
working.
I think I can. I think I can. I think I can.
A little yellow calculator.
Oh, you see it? It's moving.
Ah.
There it is.
My calculator is slow in general, so.
Look at you go, little buddy. Come on. It's like an Etch-a-Sketch, you know? You're like watching, like.
What if it just stops?
It's like and dies. It's like, ooh, it feels warm. No, I'm just kidding. It doesn't feel warm, but there it is. Okay.
No, the third one.
So, what I've just done here is graph the second derivative. Now, so visually, what should we be looking for? Well, at 0, what does my second derivative equal? 0. So there we go. That's a point of inflection, potentially, right? The second derivative to the left of 0 is what? Positive. The second derivative to the right of 0 is what? Negative. And so there it is, the graphed second derivative. Okay? No, I think it stopped. Yeah, it stopped. But there it is. Wow. Okay? So you can use your graphing calculator to actually graph those second derivatives. If you don't have this pretty type like I have, it still will work. It still does graph the second derivative. It's just, or the first derivative or second derivative. It's just a little bit trickier, that's all. But it does work. It's pretty cool. All right, so there's all that. Bing, bang, boom. Okay, that's your answer. All right. Second derivative test. Let's do it.
Let's do it.
Nope. Second derivative test is like the first derivative test because it
It just goes straight from the second response to the
it still just finds relative extrema, yeah. Concavity also allows us to determine relative extrema of a function. Okay, concavity also allows us to determine relative extrema of a function. Now, reviewing, right, going a little bit back, we talked about the first derivative test, and we used that to determine the relative extrema of a function as well. All right, so let me see if I've got like a picture here of something I could use. Yeah, okay. So I know we use these graphs for concavity and stuff, but let's look at this. So for example, in this first graph here, right, do we have any relative extrema in this first graph? Yes, we do have relative extrema. So let's call this f. This is our original function. F does have some relative extrema here. Does f have a relative maximum?
Yes.
At what x value?
-1.
-1, we have a hill. That's a relative maximum right there. Do we have any other relative maximums?
No.
Not according to the graph, right? Do we have any relative minimums?
Yes.
Yes. At what x value?
1.
1. Do we have any other relative minimums?
No.
No. Okay, so we have these relative extrema. Let's just consider the relative maximum here. Okay, remember the first derivative test, we use that. Okay, we know we have a relative maximum if our first derivative is changing from what to what? Positive to negative. If the first derivative is changing from positive to negative, that means the original function is changing what kind of behavior? From increasing to decreasing. And sure enough, we're changing from increasing to decreasing there. So we would expect in our first derivative, okay, to be changing from positive to negative. And sure enough, if we go over here, the first derivative is changing from positive to negative, right?
Yeah.
Okay, cool. So we go to the relative minimum, okay? Using the first derivative test, okay, looking at the first derivative, to find a relative minimum, we want to see when the first derivative is changing from what to what? Negative to positive, okay? And sure enough, at 1, the first derivative is changing from negative to positive, okay? How does the first derivative changing from negative to positive, how does that translate to the original function? The original function would be changing from decreasing to increasing, and that creates that relative minimum. Now, how then can we use the second derivative to determine when we have a relative maximum or relative minimum? Okay, so we don't need the point of inflections, but what is the second derivative? What have we been using the second derivative to find about the original function? Points of inflection, also what else? Okay, when the second derivative is positive, that means the original function is what? Concavity, right? Concave. When the second derivative is positive, the original function is concave up. When the second derivative is negative, the original function is concave down. So how can we use concavity to determine whether we have a relative maximum or relative minimum? Does concavity link up with our relative extrema here? How? So I kind of hear some things there. So yes, the concavity determines the shape of the function. At a relative maximum, what type of concavity will we always have?
Concave down.
Concave down, like a frown. Okay, and then at a relative minimum, what type of concavity do we always have? Concave up, like a cup. That's right. So we can use concavity to determine whether we have relative extrema or not. Okay. All right. So let's say that. Okay, so the second derivative test is basically that. Now, it kind of like, well, this may raise a question in some of your minds about the utility of this, and I'll explain why it is useful. Yes, sorry, thank you. So let f be a function. Of course, you might always ask the question why this is useful, but I understand that. All right, so anyway, let f be a function such that f prime of c equals 0 and f double prime exists, okay, on an interval containing c. So the double derivative of f exists on an interval containing c. Whoops, and I forgot. Okay. So f double prime, that's like legit, and then Connor's title is f double derivative. Double derivative of f, which I'm sure is a thing. It is now, at least. He's coined it. That's right, he's coined a phrase. That's right. Every time I say the the double derivative now, Connor will be like cha-ching, so. That's right.
I make the money.
Jack's not here because it's his birthday, huh?
No, he's trying to
He's in the ER.
In the ER on his birthday right now.
So we should think
Happy birthday to.
He's gonna watch her.
Oh,
Wait, does he actually?
Jack, I'm sorry. That's terrible. We'll sing later. We'll sing at the end, not now.
Terrifying.
Put it in the note.
Because that means that if he can get kidney stones, I can get kidney stones.
I have one.
All right, folks.
I don't want to get it.
That's terrible. I'm so sorry to hear that. That's got to be the worst pain ever. All right, so
You never wait.
I never had one. No.
My dad gets them all the time, so I'm just kind of waiting
Determine the absolute
for it to
maximum
happen.
speed.
Gosh. On a scale of 1 to 10, 11. Okay.
On a scale of 1 to 10.
If f prime prime of c is greater than 0, so if that's true, if the second derivative is greater than 0, which means the original function will be concave.
Oh, f prime of c is greater. Oh, then it'll be concave. Yeah.
Right, because if the second derivative is greater than 0, it means it's positive. Positive second derivative means the original function is concave up. Then c f of c is a relative minimum. Right, concave up like a cup, that indicates a relative minimum there, right? Concave up like a cup, relative minimum of f. Okay, if f prime prime of c is less than 0, then c f of c is a relative. Right, again, so if f prime prime c is less than 0, that means the function will be concave down, so down like a frown. That means a relative maximum, right?
Down with the frown that Jack has on his face right now.
Ooh.
Well, maybe he's passed it already and he's just recovering.
And he's smiling. Dude,
I don't know, maybe.
Did they put you in the past kidney stone?
Dude, I would take heroin to pass a kidney stone.
Did you hear that, Internet?
Some superintendents would be like, oh, what up with the notes? How nice, and they'll just watch that and say that.
Oh my gosh. What kind of class is this? All right, there's one more situation, right? We said if f prime prime c is greater than 0,
What if it equals 0?
then it's relative, right? If f prime prime c equals 0, though, that is possible. Okay, if that happens, the test fails. Okay, inconclusive. Try using the first derivative if possible. Sorry?
So, you made it exclusive, but it could still have relative.
Could be. We just don't know. Because if it equals 0, that means we possibly have a point of inflection there too. And sometimes the relative extrema could also be. Oh, never mind. Relative extrema couldn't be a point of inflection, I guess. Never mind. Anyway,
Well,
I don't know.
To do the test, you have to find the zeros, do the test.
Right.
So if you got 0, wouldn't that just
Actually, you don't need to use the zeros to do the test. You don't. Because we'll get into it. Well, I'll show you here. I'll show you here in just a second. Okay? You want to find the critical points. We're saying the first derivative equal to 0. then you take those critical points from the first derivative and plug them into the second derivative.
Okay.
So let me show you. Let's just show this. We're going to do one example, and then I'll get you guys started on your assignment. Okay?
Is it like a full page example?
It's like a third.
I have 5 lines at the bottom of my page and make it work.
I believe it.
Kept 2.5. Flip it. I guess the question about utility that you anticipated is why not choose the first derivative?
Right, so Austin's question here, and he's exactly right, okay, and let me get this written down, but the basic idea is like, Mr. Wid, why bother using the second derivative test if we already have to find the first derivative in the first place to then get the second derivative, right? And he's right, I mean, you're right, we, in general, right, if we're just like going about this the normal way that we do things, okay, if we go about the normal way that we do things, then you would just normally just use the first derivative test.
Is that what NASA, so when the NASA scientists are trying to calculate something about how Saturn
You're
just
closer and closer to 95%.
circles the sun or something, they use the first derivative test, not the second derivative test.
All right. There are applications for this, I mean, as far as like what we'll be seeing, and there are ways I can force you to use the second derivative test.
Like, say on a test, use the second derivative test.
Right.
Using this.
Well, I mean, for example, if I were to just give you the second derivative and say, here, this thing is the second derivative of a particular function, and then here are some critical points for that function. Tell me whether the function has relative extrema or not at those critical points. So that would require you then to use a second derivative test. You wouldn't be able to use the first derivative test because if I give you the second derivative, we don't know how to work backwards yet to find the first derivative. Okay.
Anti-derivative, actually.
Well, no, we're going to get to that point. So, but believe it or not, though, there. I mean, well, not believe it. I mean, not. I guess you could believe it. Okay. Right. Working backwards. Sometimes working backwards, we don't know the answer for working backwards.
Yeah, because we get C.
Well, not only plus C, but I'm saying like sometimes we can't work backwards. We just don't know how to integrate that thing.
So, question then.
Yeah.
So, does that mean that like all critical numbers are points of concavity or something like that? I guess there a
Not
relationship
necessarily,
between them,
no. No, because critical numbers we find from the first derivative and then the second derivative, it could be completely different numbers then.
Okay.
So, all right, here we go. So, first things first, if I want to find the relative extrema of this function using the second derivative test, okay, according to the second derivative test, I need to get some points C such that f prime equals 0. Okay? So the first step here, I got to take my function and do what? Take the first derivative. Yeah, find the first derivative, which is going to be negative 15x to the 4th plus 15x squared. Okay, set it equal to 0 to find those critical points. I'm going to factor out here. What can I factor out from these two terms?
Negative 15x squared.
Yeah, good. A negative 15x squared would probably be a better way to do that. Okay. So, we set each factor equal to 0 there.
True.
And we solve for x. We get x is 0 here. And we get x is plus or minus 1. Okay? So those are critical points. Now, if we were using the first derivative test, our next thing would be to do the number line with f prime. We'd put negative 1, 1, and 0 on there, and then look for when the first derivative is positive, negative, negative, positive, all that stuff. Okay? But we're not going to do that. We're going to use the second derivative test. So we go to f prime prime. Okay? We get negative 60 x to the 3rd plus 30 x. Yes?
Yep.
Okay? And now, I am not going to set this equal to 0. I want to now just test. I just want to test all my critical points. So I'm going to find f prime prime of 0. Okay, what is f prime prime of 0? 0, which means the test fails.
Now we gotta go do the first derivative.
Okay, right. F prime prime of 1, though, it will be negative 60 plus 30, which is negative 30. And so that means the second derivative is negative at this critical point. A negative second derivative means what type of concavity in the original function? Concave down. And so what type of relative extrema? Relative maximum. At x equals 1. Okay, relative maximum, sorry, of f. Okay. And then f prime prime of negative 1. Let's see here. Negative 1 cubed is negative 1 times negative 60 is positive 60. Negative 1 times 30 is negative 30. So I get 30 there. And so f prime prime of negative 1 means our second derivative is positive at negative 1. If the second derivative is positive, that means the original function is concave up. Concave up, so we have a relative minimum. This is why those fundamentals, understanding those fundamental concepts, negative second derivative, concave down in the original function. Positive second derivative, concave up in the original function. Those fundamental concepts can just lead and guide you and to help you then kind of figure out your answers here. Okay?
Can we see the graph of this?
So let's pause on seeing the graph just yet. So the test failed at 0. Let's see why it failed, if we can maybe figure out what's going on here. So let's go back to the first derivative here, and let's just do a quick first derivative test at 0. Okay, let's just see what's happening at 0. I'm not going to worry about what's happening to the left or right of negative 1 and 1. Let's see what happens between to 0. So let's go, let's see, negative 1/2, I guess, here, negative 0.5. Okay, if I plug negative 1/2 in, negative 1/2 squared is positive 1/2 times a negative 15, so it's going to be negative. And then negative 1/2 squared is positive 1/4. 1/4 minus 1 is what? Negative. Negative times a negative, positive. Okay, f prime of 1/2. 1/2 squared is 1/4 times negative 15, still negative. 1/2 squared is 1/4 minus 1, negative. Negative times a negative, positive.
So nothing happens.
So yeah, there is no relative extrema at 0, okay? There is no relative extrema. Since negative 1, by the way, since negative 1 has a relative extrema, okay, it's a relative minimum at negative 1, what would we expect to be the sign over here? Negative. And then since 1 is a relative maximum, what do we expect the sign to be over here? Negative. Yeah, very good. Okay, and if we calculate it, it would be true as well. All right, let's see the graph just to kind of figure out our last... Oh, my poor little calculator there.
It's kind of weird that like the maximum has such a smaller y value than the... Excuse me. Yeah, the maximum has like such a smaller y value than the minimum.
Sorry. What were you saying again?
I was saying like because our maximum is like very negative.
Our maximum is very negative.
Yeah, and then our minimum is very positive.
Oh, as far as like the second derivative, you mean?
Yeah.
It's just a very steep concavity, a very like, so like you can have concavities like very like wide, you know, kind of like more umbrella-like, and you can have very sharp concavities too. And I think the larger the number, the further from 0, I should say, the sharper the concavity. You can see it's more sharp.
Yeah.
All right, folks, let's look up here real quick. So here's the original function. Okay, there's the original function. Relative min at negative 1, relative max at positive 1. At 0, not a relative min or a relative max. Although, what would we say happens at 0? What do we call that? Can you see it? What do we call? What would 0 be? It's one of our special points. It's a point of inflection. We're changing from concave down to concave up. Okay? And also, there's another point of inflection like somewhere in here as well, because we're concave up right here, and then it changes to concave down. So there's another point of inflection here, and let's say there's another point of inflection again somewhere in here, because we're changing from concave up to concave down. Okay? So there's 3 points of inflection. Sorry?
So, like from 0 to like wherever that point of inflection is, to the positive side, it's actually concave up and concave down.
Yeah, so listen up here, folks. Yeah, we're changing concavities here, from concave up immediately after 0 to then concave down for the rest of the interval there. Can you see that okay? Yeah. Yep, pretty crazy. And actually, it would make sense. If we were to actually like set this equal to 0, find the critical points, we would find 3 numbers there. This was for the first derivative test. So we were only checking the critical points from the first derivative. We would have a separate check for the second derivative, for the critical points, or for the points of inflection. Okay. Any other questions? Well, we'll see. I don't know. I'm going to see what we've got. Okay. I was going to give you no homework for anyone. Since you asked for a small homework, you got
I wasn't playing on
We actually have no
it. Don't we?
No.
We've never not.
Mr. Wood, when's our test?
That's a good question. I am not exactly sure yet.
Anyway, we're chill.
It's going to be before winter break.
What is it?
Our next
Good. So we'll get one more weapon and chill.
Two more tests.
What is the last day of this class? Or not, excuse me, of this term.
I was gonna say, this class doesn't end.
Yeah, I know. Keeps on going.
I don't know what the last day of the term is. I think it's like December 20, or no, January 20 something or something.
My second semester is going to be this.